Hi everyone, welcome. Let's get stuck into it. I'm Hayden, I'm joined by my colleague Tom, and today we're going to be running through enhanced input in Unreal Engine. So we'll start with some super brief introductions and just why we're giving this talk today. Then we'll jump right into enhanced input. We'll start with a pretty basic overview and implementation, and we'll progressively get a bit more complex. In particular, Tom's going to pick apart Lyra. There's some really good learnings there. And then we'll cover a couple other interesting ways to use enhanced input, and we'll follow on with some real-world situations we've seen in the wild where developers have struggled a bit with enhanced input. All right, so who are we? Tom and I are both directors and software engineers at Prismatic Studios. We're an Unreal Engine technical consultancy and code development studio based in Auckland, New Zealand. We're primarily a service-based studio, which means we've had the opportunity to work with clients on a huge range of projects and industries. I'd hazard a guess that maybe it's the majority of industries that Unreal touches. We're also an Unreal Engine Gold service partner and a UDN partner. So there's a good chance if it's not Epic answering your UDN cases, it could be us, particularly if it's enhanced input cases. So that's a pretty good tie into why we decided to give this talk. We've seen on the UDN there's a huge demand for enhanced input support from the community. And there's a huge range of the exact type of support that's needed as well. There are teams that have worked in UE4 for years. They're just getting acquainted with UE5 and being faced with the prospect of moving into enhanced input. And then we've got teams that are a bit more experienced. Maybe they're looking for best practice guidance or just getting a particular feature working. So it's our hope that we can try cater to as broad of a range of enhanced input users as possible here. We're going to start with some really core concepts and a basic implementation. Then we'll work our way through all the way to some real world scenarios. So with that being said, hopefully there's a little bit of everything. There's something for everyone in here. But apologies in advance if you're already pretty familiar with enhanced input. We're going to be starting from a pretty foundational level to start with. Okay, so the core pillars of enhanced input. I should probably just preface this by saying that enhanced input is the de facto method of handling input in Unreal Engine at the moment. So first of all, it's very asset-centric, and I'm referring to data assets when I say this. I'm sure that anyone that's used data assets know just how powerful they are. And when you think about defining things in your project, for instance, how input should be handled, they're a pretty natural pick. Next, enhanced input lets us do a whole lot more than just defining input schemes. There's a lot to talk about here. It's essentially the whole talk. But it lets us dynamically change how input is handled based on game state. We can pretty elegantly support a huge range of input mapping contexts and input actions. We can do player remapping, of course, and we can do neat stuff like injecting input. So enhanced input is also backwards compatible with the legacy action axis mapping system. There's not too much to say here besides that if you want to take advantage of that, there's a couple of project settings to be mindful of. And lastly, we can encapsulate enhanced input super easily. We can even go so far as to putting all of our input logic into gameplay feature plugins or various segmented parts of it, which we can then go on to turn on and off. And there's quite a few advantages to that. We also don't need to modify the base game in any way, which could be quite good for something like content delivery. So just by going through the core concepts, you've probably got a good idea of how it stacks up against the old action axis mapping system. The legacy system does about what it says on the tin, and that's it. You can define hardware input mappings to names and some common keys to combo with. If you want to do anything more than that, you're going to have to delve into modifying INI files most likely. Compared to enhanced input, it's modular. It can be used in a pretty dynamic way. We can do all sorts of comboing with quartered actions and combo actions. And there's a whole heap of quality of life improvements, I should say, like dead zone support, which is one of the pre-made input modifiers. So anecdotally, the reception I've seen to enhanced input is that there's a bit of a learning curve. Maybe it takes some more time to set up in the legacy system. So with that in mind, we'll speed run a bit of enhanced input setup. And to really showcase my artistic ability, we'll be handling input for a physics-driven marble. So I'm sure you can tell I'm an engineer. So we'll start with the input actions, which is what we use to allow the user to do things in our game or project. So these are one of our data asset derived classes. They let us propagate a value of a particular type, so a Boolean or an axis or a vector and so on. They let us define the triggers which control the state of the input action, and modifiers which are performed on the raw input values in succession before they reach any input listeners. So for our marble, we want the user to be able to roll it around, look around, jump, and naturally perform aerial attacks. So I've gone ahead and split up the rolling into 2 input actions just for this example, just because it's slightly easier to handle both gamepad input and mouse and keyboard input this way for WASD. So starting off with the rolling input actions, like I said, we've gone with an axis 1D type so that we can separate our WS and AD keys and still have that work well with the gamepad analog stick axes. We've gone with the down trigger, which you don't actually need to specify since it's the default trigger type, although you would want to explicitly specify this if you're going to use an actuation threshold other than 0.5 or change any other default values. And we're also using a dead zone input modifier here since we're planning on using this with an analog stick. Much the same with the look input action. The only difference here is that since we can use a mouse on the keyboard and mouse side of things, we only need the 1 input action and an axis 2D type. All right, so the jump is a simple Boolean type, which is the equivalent of an action mapping in the legacy system. Usually this would probably be a press trigger or something similar, but we've gone with down here, purely just because we can trigger this off the started state and get almost the exact same implementation, but we can trigger it for longer, which is useful for triggering chorded actions off it, which is something we want to do with the aerial attack because we only want to do an aerial attack when we're triggering a jump. And like I said, in the attack action, we're using the jump as a chorded action, meaning we have to be triggering the jump in order to in turn trigger an aerial attack. Full disclosure that if you've used enhanced input, you probably realize this isn't a perfect implementation, but I think it gets the ball rolling, no pun intended, to give us a bit of an understanding of how chorded actions work. So moving on to our input mapping context. IMCs let us represent a collection of input actions that can be used in a given scenario or context. We're just exploring a minimal example here today, so we just need the 1. But there's a lot of scenarios where you want more than that. You might want to specify some hard-coded alternative input schemes ahead of time, or otherwise you just want multiple as they relate to different characters, modes, or tools that a user can use. And we get all this flexibility by the fact that we can add and remove these at any point in runtime and change the priority over one another. So for this particular IMC, we've just gone with a very stock standard keyboard and mouse and gamepad input scheme. And the only thing to really note here is that IMCs as well as input actions can hold triggers and modifiers. As you can see with the one of each of the pairs on the WS and AD keys, we just use a negate modifier to trigger a value on the other end of the axis. Okay, so in the player controller, we're adding our IMC on begin play just with the enhanced input local player subsystem. We could also do all of our input listening here as well if we wanted, but just because I'm performing logic on the pawn in this example, and we don't really know what the pawn could be theoretically, it's probably best done with an interface, and I've just forgotten an interface for this example. All right, so the pawn itself, this is probably a bit hard to read, but that's all right, I'll just narrate over the important parts. So this is where we have our input listeners, which I've just learned that James doesn't like these blueprint event input listeners, so I'm sorry, but this isn't production code. So the most important part is that we can trigger functionality off a given state in the input action. So most of these are going off the triggered state, except for the jump action, like I mentioned previously, we're just going off the started state to avoid triggering a whole heap of jumps while we give the user time to perform a chorded aerial attack action. It's also worth mentioning that none of this logic has to be in a player controller or a pawn class. Particularly in C++, there are a whole other bunch of options that architecturally might make sense. For instance, you might have programming subsystems that deal with a given mode or tool, and it's totally fine to put that logic there. After all, input doesn't only have to relate to player characters. Okay, and that's all we need to get our marble rolling around. And you can probably put this together in even less time than it took me to explain the slides. And we're in a pretty good position to expand on this implementation from here.
Cool. So now that we've covered a basic understanding of how enhanced input can be set up, we're now going to take a look at how Epic has implemented enhanced input themselves in the Lyra sample project. So for those of you that are unfamiliar, Epic Games has put together the Lyra project as a comprehensive example of best practices and implementation techniques in UE. And we can investigate this project to learn how some of the best practices could be implemented for enhanced input in our own projects. So let's take a look at the Lyra project and see how Epic has leveraged enhanced input in the shooter core example. So in the Lyra project, one of the first areas of interest is the mapping of input actions using gameplay tags. Gameplay tags are user-defined strings that function as readable hierarchical labels, offering a flexible way to organize and manage game content. You can define gameplay tags in a number of different places, but in general, you need the tags you define to be added to the tag dictionary for the engineer to be aware of them. Looking closer at the example on screen, inside of a Lyra input config asset, we are able to define which input actions are associated with which input tags. On screen, you can see that the input action jump is associated with the gameplay tag input tag.jump. In the basic setup, we defined the behavior of an input action by binding it explicitly within the pawn blueprint. But Lyra adds a layer of separation by binding an input action, adds a layer of separation to the binding of an input action by instead binding the input action to a gameplay tag instead. At the start of gameplay, the local user's input is initialized and read from this input config asset. And within this the Lyra input config asset, which is shown on screen, it contains arrays of input actions and the associated tags that they will be bound using. And so by binding to an input action using a gameplay tag, instead of a reference to the asset itself, it allows us to decouple changes to the input action from the binding logic. And so by binding to input tags, Lyra maintains the binding in C++, which provides us the flexibility to configure the input action or the action config asset within the editor. It also ties in very nicely to the gameplayability framework, which we'll touch on later. And since this binding is now only maintained by this tag, we could theoretically swap out the input action asset to a completely different action, and the functionality called when the input is triggered would remain consistent. But more importantly, we would only need to make that change in one place, inside of the input config asset, rather than inside of blueprints or C++ files. So the first data structure that's relevant here is the Lyra input action struct. The struct just maps an input action to a given gameplay tag. And then probably the most important addition to support the ability to map input actions to gameplay tags is the Lyra input config data asset class. So this asset is used to define an input configuration that maps all of the input actions it contains to a gameplay tag. It also provides some helper functionality that can be used to get an input action from a given gameplay tag. And you may notice that in this class we have the option to define either native input actions or ability input actions. And again, we'll come back to this a little bit later, but native input actions are actions that are bound to native functionality within, in this example, the Lyra hero component, but ability input actions are bound to gameplay abilities. And so when we look inside of the initialize player input function, this is inside of the Lyra hero component in this example, we can see how native actions are bound using a gameplay tag and are bound to functions declared within the component itself. So this is where basic functionality like moving the character or looking around with the camera is defined. But when we look closer inside of the bind native action function, we can see that the input action which is actually bound here is just whatever input action was tagged with the gameplay tag in that given input config asset. And so our end result is pretty similar to the basic setup. When a user makes an input as defined in the input mapping context, the expected output is displayed in-game. However, the system is built in a way which is more flexible and less reliant on hard references to the input action assets themselves, and we can make changes to input actions in cases entirely removing old ones and replacing them with new ones, and if they are marked with the same gameplay tag, then the binding will remain consistent. Cool. Another feature that Lyra makes use of and provides us an example use case for is for utilizing different input mapping context priorities. As we saw earlier, an input mapping context serves as a mechanism for defining input actions a user can make for a given gameplay context. And while simpler projects may consolidate input actions within a single context, Lyra demonstrates the advantages of having multiple contexts for more complex scenarios. For instance, a character could have different modes of travel, like walking, swimming, driving vehicles, and it would make sense to have distinct context for each. And by managing contexts dynamically, we can add or remove them from the local player based on the game state. And this approach prevents input collisions and ensures that only relevant actions are triggered when a user input is used for different input actions by mutually exclusive input mapping contexts. But how would we determine which of the multiple input mapping contexts will handle a user input if multiple input actions could be awaiting the same key press or the same input action? Well, it comes down to the given priority of the multiple input mapping contexts. In the system, whichever input mapping has the highest priority takes precedence and handles that user input. However, if there is no input action associated with that input within a highest priority context, the input is then passed down to the next input mapping context in the hierarchy to be handled. And this prioritization mechanism ensures that user inputs are processed in a predictable and structured manner. So let's take a look at a situation where this is actually used. So inside of the Lyra shooter example, we encounter a practical application of this, of using multiple input mapping contexts. On screen, you can see the two input mapping contexts that are related to the shooter character. The first mapping context, the input mapping context shooter game, which let's just call it the default shooter context, encompasses actions like movement, aiming, and shooting, which are fundamental to the gameplay experience. However, there's another context called the IMC ADS speed, which is added to the user specifically during aim down sights or ADS mode. When the player aims down sights, the additional context is added, allowing for specialized input handling related to aim down sights. Both input mapping contexts contain the same input action, the input action look with mouse and stick, and the input actions are associated with camera movement in both cases. But by handling the input in a different input mapping context, it makes it very easy for us to add different input modifiers to the same input action. And in the example on screen, this is exactly how input is handled while in aim down sights mode. An input modifier has been added to the input action look mouse input within the aim down sights context, which changes the behavior of the same input as defined in the default context. And so when we look at the aim down sights mapping context asset in the reference viewer, we can see where in the project the additional input mapping context is being added to the enhanced input subsystem. And in this example, it's being added during the gameplay ability aim down sights. As a quick note on this slide, I've come across some discussions online about where the best place to add input mapping context is from an architectural point of view. And both in Lyra and in my own experience, it's generally appropriate to add the input mapping context from whatever context it's representing. So in this case, it makes sense for the for aim down sights, we apply the mapping context during the gameplay ability, as the ability is a self-contained object representing that game context itself. And then inside of the gameplay ability, we see that the aim down sights input mapping context is added with a higher priority than the default mapping context, so that the aim down sights speed modifier is applied to the camera movement inputs, giving the user more precise camera movement during the aim down sight state. And so on screen, you can actually see the result of adding the additional input mapping context during the aim down sights gameplay ability. While I'm holding the right mouse button, my mouse input feels dampened, and the camera moves slower, giving me more precision about where I aim. So this is actually accomplished by using an input modifier, which is applied to the look input action. And we mentioned input modifiers a little bit earlier in the talk, but just for a quick recap, an input modifier is a preprocessor that actually alters the raw input values received by Unreal Engine before they are then forwarded to input listeners. Each input associated with an input action undergoes, a series of these modifiers in the order that they are applied in the input mapping context, with the output value of each modifier becoming the input value of the next. So let's look at the aim down sights example again and see how this input modifier was created and then applied. So inside of the aim down sights input mapping context, we see that the look input action is mapped both to mouse and gamepad inputs. And we also see the setting-based scalar modifier is being applied to the input action. The setting-based scalar modifier is a custom input modifier created for the Lyra project, and this modifier is intended to scale raw input based on a property saved in the shared user settings. The key function we want to override when inside of an input modifier is the modify raw function, which is where we can write logic that will actually alter the raw input values. We pass in a couple different parameters to modify raw, but of particular interest is the input action value, the current value parameter. This value is the input value that will actually be altered within this modifier, and depending on the order of modifiers that is being applied to this value, it'll either be the raw input value of the device, if it's the first modifier in a chain, or it will be the modified value of the previous modifier, if it's deeper than the first modifier in a chain of multiple input modifiers. So inside of the modify raw function, we see that the aim down sights functionality is just implemented through input value clamping. When the input modifier is added to the input action in the input mapping context, it exposes a number of custom parameters to us. In this case, the X, Y, and Z axis scalar setting names. These properties are then found in the input user settings and used to clamp the raw input to a range of values that is more appropriate to the intended feel of aiming down sights. The modifier then returns this clamped input value. And then once the input value is returned, it'll either be modified further if other modifiers are applied to the action, or it'll be passed off to the bound functionality awaiting the input. And so here's another short example of where input modifiers are used during the Lyra shooter example. This should be a pretty familiar setting that is present in almost all first and third person games, which is giving the user the ability to, invert the camera controls based on their preferences. So this inversion functionality is again achieved using an input modifier. The Lyra project again includes this custom input modifier, which can be applied to an input action called the Lyra aim inversion setting. And we see that this input modifier is again applied to the look action in the default input mapping context. But some of you in the crowd with eagle eyes may have spotted a difference between the input action modifier declared in the default mapping context and the aim down sights input mapping context. And what you see on screen is the difference in behavior when the look action in the default mapping context does have the Lyra aim inversion setting applied. It's a little bit hard to make out on screen, but this is me moving the mouse up in both cases. So it's inverted, pointing downwards, and then when I aim down sights, it actually looks upwards. While this may be considered a bug, I think it's also a perfect learning opportunity for us to explain, why this is happening. And since the input mapping context with the higher priority is consuming the input for the look action over the default mapping, only the modifiers of the aim down sights mapping are applied to the raw input. And since the aim inversion modifier is missing from the aim down sights mapping, the inversion is not being applied to the input. And funnily enough, when I was giving this talk to the rest of our team internally, we found out why this is the case, because the bug was actually logged for another reason. It happens to be that currently, I believe in 5.3 and maybe even 5.4, if in two input mapping contexts, the input action is the same, and they also apply the exact same input modifiers, regardless of what custom properties you're passing into those modifiers, the engine will register that there's been no change, and it will actually handle the lower priority input mapping context action instead. But I've been told that there is a fix for that coming in 5.5, and if you want any, ways around that, you could either reorder any input modifiers, or you could just add another input modifier that technically does nothing, but as long as it's different than the base modifier, it should fix it. But I believe this is the band-aid fix in Lyra at least. So when we look at the aim inversion input modifier in C++, we see that the modifier follows the same structure as the setting-based scalar modifier. The modify raw method has been overridden, and the implementation of the function shows the following. The input modifier gets the shared settings for the player and checks the settings to determine if the user has enabled either vertical or horizontal axis inversion. If the setting's enabled, then the input is negated in the relevant direction, effectively inverting the input. And then after applying any necessary modifications, the updated input value is then returned from the function. And this results in a pretty clean and self-contained implementation to read from a user's input preferences and then easily alter the raw input value so that the functionality that awaits this value remains consistent and ultimately doesn't care if the input was inverted or not. So, as you may have picked up in the last two slides, a design pattern is employed where input modifiers dynamically adjust input behavior based on a user's custom settings. And this approach allows players to toggle input preferences to suit their individual playstyles or preferences. By reading from the user settings, input modifiers can modify raw input values at runtime, allowing for modifiers to query the user's preferences and then alter the raw input of the device to allow for customizable input behavior. So let's look at how this design pattern is implemented and how we might be able to implement a similar pattern in our own games. Oops, this way. So inside of the aim inversion modifier, which we looked at previously, I've just highlighted two function calls that kind of demonstrates this pattern. Here we see that the raw input value will only be inverted based on a property stored inside of the user settings. And then when we look inside of the user settings class, we see that there are actually a large number of input related settings that could be toggled on or off by a user to allow for more customizable control schemes. So if you're looking to kind of replicate this approach in your own input system, you could kind of follow this process to do it. Well, firstly, you'd want to create a user settings UI that's accessible to your players. This interface should offer them the ability to tweak various input settings like sensitivity, axis inversion, or anything else you could think of as relevant. Think about making it intuitive and user-friendly so that players could easily customize their experience. And then once players have kind of adjusted these settings to their liking, you'll need to save them somewhere persistent. This class could probably store all of your customized input preferences. Just make sure that any changes made in the UI are saved properly so that users don't have to keep resetting their preferences every time they log in or launch the application. And then comes the fun part. So you want to then read these user settings in your input modifiers. These modifiers are what actually tweak the raw input values based on what that player has chosen. And then that should dynamically adjust things like sensitivity or inversion on the fly according to their stored preferences. And there you have it. With that set up, players have full control over their input experience. Whether they prefer high sensitivity or inverted axes, they can tailor their game's controls to suit their needs. So it's all about giving players the freedom to play the way they want, ultimately leading to a more enjoyable and inclusive experience for your end users. And lastly, let's take a look at how Lyra binds the activation of gameplay abilities using enhanced input. In Lyra, gameplay abilities are triggered by input actions, providing the communication between player actions and in-game mechanics from being triggered. I expect many of you have utilized the gameplay framework in your own projects before, but one major advantage of binding input actions using gameplay tags is how well it ties into the overall gameplay framework, and in particular, the activation of gameplay abilities. On screen, you can see that the gameplay ability dash is being triggered using the shift key. So let's see how this is implemented. So the first area to focus on again is that Lyra input config asset, which is we're able to define which input actions are associated with input tags. Again, we see that the ability input actions are separate from the native input actions, which means that these input actions are expected to trigger a gameplay ability action instead of native logic within the input system or its owning player. So these input actions are stored in a separate array within this config asset as they are bound differently. Other than that, you can see on the right that the input action for the ability dash is pretty much just a standard input action with a simple press trigger. Then inside of the default input mapping context, the input action is mapped as usual, in this case to the left shift button or to the left thumbstick button on gamepad. But when we look inside of the input component, specifically within the initialize player input function, we begin to see how ability actions are bound differently to native actions. The function highlighted on screen, bind ability actions, serves a distinct purpose that differs from bind native action. Unlike bind native action, which directly binds individual input tags to functions, in this case within the Lyra hero component class, bind ability actions takes a different approach. Instead of binding to specific input events, the bind ability actions accepts an input configuration, which is that data asset class that contains gameplay ability input actions, and binds all of those associated actions to the input ability input tag pressed and input ability input tag released functions. These events are then responsible for triggering the actual functionality based on the associated input tag. When the bound ability input tag pressed function is called, it serves as a bridge between the input system, sorry, did I skip a slide? No. Sorry, between the input system and the Lyra ability system component. The function takes a gameplay tag as a parameter, in this case the input tag, and represents the tag associated with the pressed input action. Once the Lyra pawn extension component is obtained, and from there they access the Lyra ability system component, we call ability input tag pressed, again passing in the input tag as the parameter. So now we've kind of got the communication to the ability system component, and we know that an input has been pressed, and we know which input tag was associated with that input action that was pressed. So within the ability system component, in the ability input tag pressed function on screen, the component then searches through all active abilities to identify any that contain the same input tag as the one that was just pressed. If a match is found, indicating that an ability is associated with that given input tag, the function adds the abilities handle to both the input pressed spec handles and input held spec handles arrays, and this allows for the ability to actually be activated later on in the frame, as these handles will be used to trigger the activation of those corresponding abilities. And so the last piece of the puzzle is how do we associate a gameplay ability with a given input tag? Well, you can see on screen that inside of that gameplay ability hero dash, an ability trigger has been added which allows for a trigger tag to be defined. And this will be defined as the same gameplay tag that was defined in that input config asset. Cool. And so the end result of this modular approach to gameplay code and input functionality is that we as developers can build flexible and extensible frameworks that, I guess, seamlessly integrate gameplay mechanics with player input. So breaking down gameplay mechanics into modular components like abilities and ability systems allows for easy addition, modification, or removal without disrupting other aspects of the game. And similarly, modularizing input functionality enables the association of specific input actions with gameplay mechanics, allowing for customizable player controls without the need of extensive reworking to the input system. But ultimately, this modular design allows for independent development of different parts of the gameplay framework and the input system. Cool. So now at this point, we've got a pretty good idea of how to best make use of enhanced input, but let's look at a couple more interesting ways that we could take it even further. Well, one way that we could extend enhanced input further is by building our game content using modular game features and incorporating the relevant input functionality within these plugins. Game features and modular gameplay plugins provide developers with tools to create standalone features for their projects, and building game features within these plugins gives us quite a few benefits. Firstly, it helps us keep our project's codebase clean and readable, and it helps us avoid accidental interactions or dependencies between unrelated features, which is crucial for developing live products that evolve their feature sets over time. Furthermore, enhanced input functionality can also be modularized within these game features, allowing for each feature to include the relevant input configurations as it is enabled or disabled. This modular approach ensures that input functionality is tightly coupled with the specific game features, minimizing unintended interactions between different parts of the game. And as a result, we can effectively manage input configurations within each feature. The game feature action add input config is a game feature action responsible for registering enhanced input player mappable input config data assets, which contain input mappings that can be added to the local player. This means that each game feature can then register its own set of key bindings relevant to that experience. And these mappings are registered whenever the game feature plugin is loaded, which allows us to change key bindings for any experience, even if it's not currently active, which is great for when we can do things like figure out on the main menu what device we're on and maybe update our UI or update our gameplay for the relevant inputs. However, the input mapping will actually only then be activated on the player when the associated game feature is activated, and it will only activate if the platform conditions are met. Inside of the game feature action, we can define a set of dependent platform traits that specify which platform this input configuration is intended to be loaded on. So for instance, mouse and keyboard mappings activate only if the associated supports mouse and keyboard platform trait is present. Platform trait maps are really valuable for defining platform-specific input mappings, particularly on platforms when you're building, I guess, an application that can be run on different platforms with varying available inputs. So for example, a modern mobile platform would have much fewer physical buttons compared to a console platform controller. And the type field also becomes really useful if you aim to extend existing functionality to alter mapping configurations when the input device changes, which can actually be, you can kind of achieve that through the common input subsystems on input method change delegate. So, oh, sorry.
All right. So enhanced input also brings along the concept of injecting input, which just means to programmatically simulate hardware input. I'll briefly touch on functional testing. This isn't a functional testing talk, which is just as well because there was a really good one just earlier today. But we just mean to use the functional testing framework in the editor here. So again, not a functional testing talk, but I've managed to sneak in a slide on it anyway. Like with any kind of automated tests, they give us confidence to modify our project however we want without having to worry about it breaking dramatically, at least as far as our test coverage is concerned. We also just have to write the test once, of course, and then they'll continue to be valuable to us throughout development, as long as the business rules they're based on don't change. So they're a pretty good investment. They're also super convenient to run, as you might have seen in the other talk, right from the editor, which isn't the case for all kinds of automated testing in Unreal. But we just need to drag in a functional testing actor into a test level, and then it's essentially just a click of the button away. They're also super convenient to write. So we just create a new actor based on a functional test. We override a few key functions, like prepare test and on test start, and put it into the level, and we're good to go. So where does enhanced input come into things with its ability to inject input? Well, I think let's just imagine a test case and sort of think through it a bit. We might want to move a player character into a trigger volume to test some kind of interaction logic. This is pretty easy. We could just use set actor location, and that would probably get the job done. But we do introduce a few assumptions here. We assume that the player can actually traverse into the trigger volume, maybe even over some terrain that we would expect to be traversable. We might have to even add some duplicate code that would be normally handled by our input handling code. For instance, the player might go from a moving state to an idle state, and that's when they can begin interaction in the volume. We kind of start to violate the single responsibility principle, if you care about that, by testing for all these things in the one functional test. But at the end of the day, we do really want functional tests to mimic the reality the player is faced with. And if we're being realistic, having one test with greater coverage is probably quite advantageous as time-pressed developers. So instead, we can inject input to mimic triggering a move input action. Because we simulated this at a fairly low level, we're also testing the move input action, any input modifiers. We can time the test or just add a timeout time to the test to make sure that player move speed is within acceptable parameters. And of course, we want to make sure that the player can actually reach the volume, maybe even over some terrain. And then, of course, we test the interaction itself too. So using input injection, we can potentially limit code duplication. We can definitely cut down on assumptions. We achieve greater coverage, and that sounds like a pretty good outcome. So as far as how we'd implement this in C++, we don't have to implement this in C++, but it's pretty convenient. In our functional test, we'd probably want to start injecting input once the test is ready to run. So we're looking to override on test start and put our injection logic in there. And for actually injecting the input, we just need to grab the player's enhanced player input object, inject input for a specific input action, and give it a value. So it's pretty straightforward. And one really quick note, we've gone surprisingly far without mentioning this so far, but there are some debug commands for enhanced input which are very useful. Show debug enhanced input displays all of the currently active input mapping contexts and the state of all input actions within them for a given player, which is definitely an essential. And show debug devices will list all known input devices along with their ID and owning user, which was also a must-have for local multiplayer projects. Okay, so now we'll do a bit of rapid fire on some real-world scenarios we've seen developers having some trouble with. The nice thing about enhanced input is that if you're comfortable with all the material up to this stage, you're probably not going to come across a problem that stems purely from technical complexity, but there are some situations where you can get caught out or it otherwise might just not be super obvious which path to take. So we'll go through a few of those. The first issue, which crops up quite a lot, is that input detection can start to get a bit spotty at low FPS. The unfortunate answer here is that input messaging is processed on tick, and it's passed to the player from the viewport client, which means that architecturally the chances of solving this on the input side are pretty stacked against you. The best advice here is just to solve the low frame rate directly, which might not be the answer you're looking for, but unfortunately there's no obscure checkbox to save the day for this one. But I think it is important to know to avoid going down any lengthy and painful rabbit holes here. But if you do happen to be a sucker for punishment, you could look at implementing a custom scene viewport or game viewport client. You could separate your input processing into another thread, which is one of these things that's easier said than done. Or if you're dealing with certain kinds of input, then you could make use of a slate input preprocessor. All right, so another thing that can crop up is dead zones apparently doing nothing, even when mapped to a gamepad thumbstick. So this is one of these situations where it's kind of you glance and you miss it. Not all thumbstick mappings are created equal. Directional mappings, for instance, your gamepad left thumbstick down, they're binary events in contrast to the axis events. So naturally, dead zones won't do anything if your values are only coming through as 0 or 1. But if you are set on using dead zones with what is essentially a directional thumbstick binding, then I'd recommend just using the axis instead and you can discard values you don't care about in the other direction with an input modifier of your own. Okay, so if you're coming from UE4 or you otherwise just haven't dealt with it yet, you probably have a few questions on player remapping. We're often asked how to do this by both, for both players and developers, I should say. And people's minds often go to just creating a whole load of input mapping contexts, but there are better ways to do it. In the latest versions of UE, we'll want to be using enhanced input user settings. It's disabled by default, but we can easily enable it in the project settings. It's save game based, which means that input configurations are saved locally, and they shouldn't be tracked by source control, although technically that's up to you, which makes it equally fit for players and developers. In the situation where you're creating multiple input mapping contexts, which stems from working on different platforms, you can make use of mapping context redirects inside of enhanced input platform data classes to handle this for you.
Cool. So next we've got another 2 questions on screen. Firstly is, can we bind multiple input actions to the same key and trigger different functionality based on the held duration? And the answer to that is yes. Inside of your input mapping context, you could simply map 2 actions to the same key. For the first action, add a tap trigger with a tap release time threshold to your desired held duration, for example 0.2 seconds. And for your second action, you'd add a hold and release trigger and then set the hold time threshold to be the same duration or higher. For, again, example 0.2 seconds. Then this setup will allow you to trigger different functionality based on how long that key was held. The second question is it possible to create a coordinate action on top of 2 individual actions? And the answer again is yes, but it's a bit more complex. Inside of your mapping context, you could map action 1 to the first input and action 2 to the second input. You'd add a hold trigger to both actions, setting the hold time threshold to your desired amount and have is one shot to be true. Then in your third action, you would add mappings to both inputs. In these actions, you would include a coordinate action trigger to the other input. And then now when you press either binding independently, or the only action 1 or action 2 would fire, but pressing both simultaneously would trigger action 3, allowing for coordinate actions with 2 individual inputs. I will say though that it gets very, very much more complex when you're having to handle release triggers, so I would have a bit of fair warning going to that one. Cool. When you're using the show debug enhanced input debugger, it's also important to consider certain factors that ensure effective debugging, especially for scenarios like local multiplayer games or projects with multiple local players. One crucial consideration for the visualization of player input is that it's on a player-by-player basis. So the enhanced input debugger provides insights into input on each player individually, and it's vital to double-check that you're actually previewing the correct pawn while you're debugging. So this ensures that the displayed input corresponds accurately to the intended player's actions, and you won't be left wondering why no input is being recognized while debugging or troubleshooting. Cool. Another question that we see commonly asked is it possible to determine what trigger was the cause of an input action if the action has multiple types of triggers? And the short answer is actually, unfortunately, no. We cannot directly determine which trigger caused an input action, but because when input actions evaluate their trigger states, they iterate through all of their triggers and solely check their state, like triggered, ongoing, etc. The type of trigger isn't actually considered within the input action itself, and this information isn't propagated elsewhere. But to address this limitation, the simplest solution is just to create 2 separate input actions, each with only a single trigger, which ensures clarity and avoids ambiguity regarding the trigger that actually initiated that input action. And lastly, how do we bind an action to an enhanced input component with custom parameters? Well, we could use the following definition on screen to define the class, parameter type, bound function, and custom parameters required. We need to specify the class and parameter type that needs to be passed into the bound callback and pass in the actual value to the bind action function itself. But then when the input action is triggered, the bound function will be called, passing the parameter we declared in the binding, in this case the true boolean to the doit function. And the advantage of doing this is that for each binding, for each trigger state, we do not need to define a new function to call. Especially if the logic is similar, we can just pass in a different argument to the bind function instead. Cool. Well, thank you all for listening. That wraps up our slides, but assuming we have time, do we have any questions?